As we move into section 7.3, first thing I want to talk about is the double angle formulas. So these are kind of nice because they allow us to take an expression like sine of 2x and write it as something that's just in terms of a sine x and a cosine x. Now these work great because you can start with the addition formulas that we covered in an earlier section, and by letting the two numbers in the addition formulas be equal to each other, you get the double angle formulas immediately. And so sine of 2x ends up being 2 sine x cosine x. So now you just need to know the sine and the cosine of 1, and you can find the sine of double that particular angle. Now cosine is kind of interesting because there's multiple forms that these things can be written in. Cosine squared x minus sine squared x. But it's also equivalent to 1 minus 2 sine squared x and 2 cosine squared x minus 1. So this one here comes from the addition formula from the last lecture, and then if you modify that using the Pythagorean identities, you can get either of these. And your text includes one for tangent as well. Tan of 2x is 2 tangent x over 1 minus tan squared of x. And that one can be proven by using the fact that this tangent is sine over cosine, and then you use whichever one of these is easiest, but you can prove this this works out as well. Your book gives you the details on that. So let's look at some explanations of how we might be able to use this. So, sort of expression you might run into in a calc class: cosine of 3x, triple, something like that. Well, if we know the double angle formula, it's actually not that hard to come up with a triple angle formula. So I could write this as cosine of 2x plus x. And if I wanted to, we have a formula from the last section that allows us to express this as a sum and product of sines and cosines from the addition formula in the last section. So this would be cosine 2x times cosine x minus sine 2x sine of x. And then here and here we've got double angle formulas for those. So that's going to be 2 cosine squared x minus 1 cosine x minus 2 sine x cosine x sine x. Now I could leave it there. I could have written this differently. I could have used one of the other double angle ones. But I'm going to see if I can get this to be just in terms of cosine x. Suppose I only know the cosine, right? I don't know what the sine is. I could draw the triangle and figure it out, but it'd be great if I could turn this just into things involving cosines so that I wouldn't have to worry about it. And it actually works out pretty well, because if I keep going from here, little distribution here and here, I'm going to get 2 cosine cubed x minus cosine x minus, and again, just distribute to multiply everything together here. I'm going to get 2 sine squared x cosine x. But I can also replace this sine squared x in terms of cosine. I have an identity for that. So I'm left with 2 cosine cubed x minus cosine x minus 2 times 1 minus cosine squared x times cosine x. And I can simplify this a little bit further. 2 cosine cubed x minus cosine x minus 2 cosine x plus 2 cosine cubed x. So in the end I'm left with this cosine cubed x up here is equal to 4 cosine cubed x minus 3 cosine x. And I could have gotten that in terms of sines, probably. I could have gotten that just in terms of cosines like I did here. Variety of different ways to do it. But the idea is that I can manipulate these things starting from only knowing one value, either the cosine or the sine of one angle, and I could work out double, triple, I could even work out quadruple that angle for the cosine or sine just using these kinds of identities. So that's one of the ones that's really helpful. The other one that we like to use is called half-angle identities. Now these are really nice. They show up in calc, and we call them a half-angle identity because what we're really looking for is a way to relate a trig function's value at one point to its value at half that point. It's also great because the half-angle formulas will allow you to take things like sine squared x and cosine squared x and rewrite them in terms of trig functions that are not raised to powers. That is very important in a calculus setting with an operation called antidifferentiation that you'll run into in the calc classroom, which is really difficult to do for an expression like sine squared. But the half-angle, you can prove that this is going to be 1 plus cosine 2x over 2. Oh, sorry, not plus. That one's minus. And this is 1 plus cosine 2x over 2. The calc operations are difficult here, but pretty easy over here, comparatively. And now, this x is written in terms of 2x over here. But I had a sine squared, cosine squared, and now I'm just left straight up with cosines. The tangent squared formula follows immediately 1 minus cosine 2x over 1 plus cosine 2x, just coming straight from the definition of tangent. So these ones have lowered the powers. Right? Squared down to nothing, squared down to nothing. But if I really want the full half angle, I can use that to come up with these and get something like this. Plus or minus the square root of 1 minus cosine u over 2. So what I did to come up with this is, if we look back here, instead of this being 2x and this x, I made this u and this u over 2. I got rid of the square by taking the square root there. And that plus or minus comes into play because depending on what quadrant you're in, you're going to get either positive or negative values. And you can do the same thing with cosine u over 2 plus or minus the square root of 1 plus cosine u over 2. So we can reduce powers with the formulas here. We can deal with half angles with the formulas here. Let's do a nice formal computation to show you what we could do with some of these. So let's try to find sine of pi over 8. Now we had from our chart sine of pi over 6, pi over 4, pi over 3, pi over 2, and the other angles that lined up with those reference angles as we moved into other quadrants. But pi over 8, not so much. But what I want to notice is that this is equal to sine pi over 4 over 2. So, using my half-angle identity, sine of pi over 4 over 2 should be equal to minus the square root of 1 minus the cosine of pi over 4 over 2. And then it's the sine function. This angle lies in the first quadrant. So I know it's going to be positive, so I can throw that out. And now I just need to finish computing this. square root of 1 minus root 2 over 2, all divided by 2. And if we simplify that, we're left with 1/2 root 2 minus root 2. So the half-angle formula allows us to compute precisely the value of something like this. It's definitely an irrational number, but because I can write it in terms of one of my reference angles, these computations from here to here to here fall out with precise values without having to use a calculator and without having to round.